Hello and welcome to our lab on friction. Now, in a previous lab, we looked at a modified Atwood situation where there was a cart on the track of mass M1 attached to a string over the pulley to a hanging mass M2. But the system mass was kept constant. M1 plus M2 was our total system mass. Now, according to Newton's second law that we examined in that lab, the system mass times the acceleration, ma, is equal to the net force. So if we write that out here, the system mass times the acceleration is equal to the net force. In this case, our system mass was the sum of the cart mass, m1, plus the hanging mass, m2. And so that was equal to our net force. Now we demonstrated there that the net force was the weight of the hanging mass, which was m2g. Now we did this and then we plotted the net force versus the acceleration, and from that, from the slope of the graph, determined what the system mass was, m1 plus m2. But for the most part, there was error there. In fact, almost everyone got a system mass that was greater than the actually measured system mass. And the reason is we didn't take into account friction. Now friction pulls in the opposite of the direction of motion. So as the cart rolled down the track, friction was pulling against it, and its acceleration was less than it should have been if it were a frictionless track. And because it had a lower acceleration, then if you don't assume that friction's there, you would think you had a heavier mass. But that's not what was going on. There was friction pulling back. So what we want to do is let's revisit that lab. Go back and take a look and look at one of your data points. And not the slope of force versus acceleration, not the force versus acceleration graph, but just look at one of the experiments where you roll the cart down the track. All right, take a look at what that net force is, what that acceleration was, that specific acceleration for that. And then take a look, and this time, let's subtract the force of friction from that. Okay? And so knowing now what the actual mass of the system is, m1, m2, and mg, knowing what those masses are, let's go back here and let's calculate what that force of friction is of the cart rolling down the track. In today's experiment, we're going to sort of repeat that modified Atwood experiment, except in this case, our cart has no wheels. In fact, it has a greater amount of friction than the cart we were using with wheels. So we really want to accentuate the friction of the cart on the track. Now, but just like before, we're going to have a hanging mass over a pulley, and using the motion sensor down here, I can observe the acceleration of this block when I release it. And so knowing the acceleration of the block, knowing the mass of the hanging mass, this is around 100 grams, knowing the mass of the cart, m1, I can again look at that relationship where I can determine the frictional force, just like we did in part 1 from our previous experiment. And so now I know the frictional force of this. But that's not far enough. I want to know what the coefficient of friction is between this box and the track. Now the coefficient of friction is a dimensionless quantity that just says how grippy is something. If this were ice on ice, it would have a very small coefficient of friction. And if it were maybe sandpaper on sandpaper, it would have a very large coefficient of friction. And so let's take a look at that for friction. We said that frictional force of friction, I'll write it like this. I'm not sure how the Dutch textbook does it, but this plays a part in slowing the cart down. And you calculated that using our equations from the modified Atwood machine. Now this frictional force is equal to this coefficient of friction, and this is a mu subscript k, and the k means kinetic. That means it's in motion. The little s would mean static, which means it's stationary. But this is moving friction, and it's always going to be pointed in the opposite direction of its motion. And so mu is the grippiness or stickiness of the interface between the box and the track. So the force of friction is equal to mu k times the normal force. Now remember that the normal force is just the force that's perpendicular to the surface. In this case, when the surface is flat, the normal force is equal in magnitude to the weight of the box itself, mg. So we'll say the normal force, F subscript n, is equal to mg. But as you begin to incline this surface as an angle, say some angle theta, gets greater and greater, eventually that normal force is going to decrease, and when it's vertical, there's going to be no normal force. No force perpendicular to the surface. The box is just going to drop straight down. And so there's a trigonometric function that sort of describes this relationship, and that is cosine. Cosine of theta. Theta is our angle up from the horizontal. So when a track is flat, at 0 degrees, the cosine of 0 is 1, and the normal force is equal to mg. However, when the track is vertical, 90 degrees, cosine of 90 is 0. So there is no normal force. But mg cosine theta describes the normal force on this box at all points in between. So if we know what the normal force is, if we know what the frictional force is, we can now calculate the coefficient of kinetic friction for this box. Now the modified outward setup is a little bit complicated. There is actually a much easier way to determine the coefficient of friction of this box. Let me take the string off of it. I just have the box. And what I'll do is, with this motion detector running, I'm going to take this box and I'm just going to shove it toward the motion sensor. Whoop. Alright, so you see it comes to a stop pretty quickly. And that's because there's a force of friction working back this way. And so as I push it up, I'm going to increase the velocity until it gets to some high velocity. I'm going to release it, and then it's going to slow down to a stop because of the force of friction bringing it to a stop. And so in this case, it's a much simpler relationship because, of course, Newton's second law says the net force is equal to ma, mass times acceleration. Well, with the motion sensor, we can determine the acceleration. We can measure the mass with this pan balance. Okay? And so our net force, the only net force acting on this, the net force is the force of friction. And so we can rewrite that to say the force of friction is equal to mass times acceleration. And we know now, if we can determine the force of friction, now we know how to determine, using, if we know the normal force, that coefficient of kinetic friction. Now the hard part about this is determining the acceleration. You think, well, that's not hard, to just use the motion sensor and look at maybe the slope of the velocity versus time graph. Well, that's one way to do it. But if you look at velocity versus time, okay, let me try that out, velocity versus time. And it's negative velocity because you're going back toward the motion sensor. Here's what happens. You get something that looks like this, okay, as you give that box a push, and when you release it, then it goes from a very large negative velocity to 0, but it does so in a very linear fashion. And so if you look at this section right here, you see that's linear as it's decreasing from your high negative velocity back to 0. And then it may do all kinds of crazy stuff. Who knows? So you're going to have to really discern and go in here and think, now where is it that the box has left my hand and is now slowing to a stop? Once you determine that, now of course you can determine the acceleration. Alright, so far we've looked at two different ways to determine the coefficient of kinetic friction between the box and the track. And so here's a third way we can do it. This time I have the track on an incline. And I've removed the pulley from the bottom of the track. That's very important. And so first of all, I want this track inclined maybe around 40 degrees or so. And how do I tell the incline? I don't have a protractor, but I do have a measuring stick. And so along this track is a measuring stick as well, is a measuring tape. And so you can determine what the hypotenuse of this triangle is. And so by determining maybe the height at this point and the height at that point. Okay, I've got a change in height and a hypotenuse. And so I know that for a right triangle like that, if I know the one side, which is my change in height, and I know another side, the hypotenuse, I can calculate my angle theta. So I can calculate the angle of incline of this track. Now that's important because remember that the normal force is equal to mg cosine theta. So as this cart is sitting on the track, its normal force is no longer mg like in the former two experiments. It's now mg cosine theta, which is less than mg. And so now gravity, of course, is still pulling downward. But as it turns out, that mg cosine theta, the normal force, is balanced by a component of gravity in the opposite direction, which leaves the net force being a component of gravity down the track. That component of gravity is mg sine theta. Now, so if I release this, the net force being mg sine theta, you should get an expected acceleration down the track. But that's not all that's happening. Because, sure, you have that component mg sine theta of the gravitational force pulling down in this direction down the track, but you have friction working the other way. And so our net force here is actually mg sine theta minus the force of friction. So once again, we can do this experiment. You've got the motion sensor. It's going to tell you what your acceleration is. So knowing the mass and knowing the acceleration, you can determine the net force. Well, that net force is equal to mg sine theta, which you can calculate, minus the frictional force. Then, knowing the frictional force, once again you can determine the coefficient of kinetic friction by knowing that the force of friction is equal to the coefficient of kinetic friction times the normal force, mg cosine theta. So that's the third and final way for you to determine the coefficient of kinetic friction between the block and the track in today's laboratory.